now we have the recording going. But yes, wait. So the first process one, is sends a prepare with the round one, because he knows that he is the leader for round one, and then the other three processes, they reply back with a promise. And this promise, this is what is meant here in the, if I can open it again, in the trust event. That's what happens when you have too many of those. It's because it's the same document. Okay, but yeah, so you see how the promise and all of these three promise, and this is kind of translated here to the trust. Yeah. So then, yeah. Well, I get. Maybe this is actually from the. Okay. Yeah. So forget about that. No, I explained it to you wrong, because this is actually called by, this is from the leader detector. So if we have the leader detector, wherever I put that, maybe I put it here. Yes. So this is a failure detector, and I guess we have a leader detector. Yes, here you see. This is the leader detector that you implemented in the labs, and they have like a return back to the application from well, which indicates which process can be trusted to be the leader. And the idea is that when your so you have like a leader detector running in your network, and then when you get the indication event from this leader detector that says that basically now you are the leader. So if by the leader detector you conclude that you yourself are the leader, then you do these steps here. So you will only send the prepare if you think that you are the leader, or you are the leader in the protocol. So I think that's maybe this is not explained fully here. Let's see. Okay. Actually, it doesn't say here, because on the single Paxos, the idea here is that you just implement like the Paxos algorithm itself, and the same with the multi-Paxos, you just implement like the algorithm itself, and then on the step here with distributed implementation, this is where you will actually use the leader detector together in the application that will run Paxos. So did it make sense for you? Yeah, the trust comes from the legal detector that. So, like actually, this step here that only if you are the leader, you will send this prepare message. There are some questions that we added. Um, yeah, like for example, this question here, question number 6. What happens if two proposals both believe themselves to be the leader and send prepare message simultaneously? Um, so, well, I I can let you think about it yourself also, but the idea is that this uh, will have the problems that um, like the round is increasing and you can have kind of an infinite loop going on because they are like always increasing the round. So if we go back to the first this one, the algorithm. Hope I have it somewhere. Yes, here. So if we go back to the execution flow. So with the preparer, if he, for example, sent the prepare and he didn't get sufficient promises back, and then there was another process that also sends the repair, and he didn't get like sufficient promises back. They would keep increasing the round, and you will never finish the phase one. So the idea behind putting the extra condition here that only the leader um, will send the prepare. It's like a liveness, or it's like a um, constraint that allows the algorithm to have liveness. Yes, because if you allowed everyone to keep sending the prepares, you could have could potentially end up in an infinite loop, and then you will never reach phase two because you don't have a quorum of promises for the same round. So yeah, was it clear about the trust? Great. And then yes, about the learner pseudocode. I don't. I can try to find. I can try to find this for you. Find the learner pseudocode. But usually the learner is the really the most easy, I would say, to often. Like if you're able to do the proposer and the acceptor, then the learner kind of falls on its own because the learner's job it's just that he will when he collects like a quorum of learn messages for the same round, he will commit to that value for that round. He will say that okay, now since I have received a quorum of learns for the same round, I will lock the value for that round and I will never change it again. So, for example, in this example, that the process 1 here, he logged the value 11 for round 3. This means that whatever happens later on for round 3, he will never change his belief. And another thing is that this learner, he doesn't send like a message to other actors for getting consensus. He is like the end, and whenever he has committed to a value, then you can reply this back to the client. And, yeah. But I will try to write this down to see if I can have pseudocode for the learning. Probably have it somewhere. Great. And about paper presentations that we had planned, like for actually the end of this month. I think that we will just drop this completely because, oh, I guess it was there. But anyway, yeah, to drop this because I had a lot of feedback from a lot of students that they think that the workload is already too high, or not too high, but enough, let's say. So I think that we can drop this after, so that because this kind of would conflict with the deadline for lab 5, which has the incorrect month on the deadline. But anyway, yeah. So I will update the lecture plan with removing this paper presentations, and yeah. So I spoke with the exam office, and you will be starting the project on this date, like the 3rd of May will be then the day where you are allowed to kind of start on the project. So this is like the deadline for the last lab. So yeah, those students that finishes the labs, they can start with the project. And unfortunately, then it means that we cannot allow like this is the final day for getting approved, and if you're not finished, then there is nothing that we can do because we cannot give you any extension past this day. So this is the day where all the labs must be delivered, because we need to send a notification to the exam office about which students have completed all the tasks. All right. So that was that. So if there are no further questions about anything, then I want to start with atomic register, because last week I think we got all the way through regular registers, and then we stopped here with the atomic registers. Yeah, so what is the difference? The main difference is that now the atomic register, it's doing what the regular register did, plus it has some extra ordering. And what is the ordering? Well, it says here in the text, but the idea is that you're not allowed to have this exactly type of sequence flow, that where you first read the old value x, and after you read the new value y that's currently being written, and then after you have read the value y, you read again, but this time you return the old value. So in the regular register, this is an allowed execution flow, but not for the atomic. So what we want in atomic is that if we read the value y, then we cannot. We need to keep reading y, or at least we cannot read an old value. Yeah. So this is the module description, and looks very similar to the regular register, but with this added ordering property. If a read returns a value v, and the subsequent read returns a value w, then the write of w does not precede the write of v. So always when, at least for me, this text description can be sometimes a bit hard to understand. So usually I like to just look on the sequence flows and see what it means. So again, we have kind of the same example that we saw previously, but now we have another process. So instead of the Q reading the wrong value, it's another process X, but the atomic register, it's valid for all the processes in the system. So this execution is also not allowed because the value y was read, and then any other process cannot read the old value. So in the regular register, this could happen. Yes. And same can happen in the majority voting algorithm that we saw, that was for the fail silent. And here we can go, the details are not so important perhaps, but so if you in the example here we have a form of p, q, and r, so that the new value p check in. Yes, I saw that the deadline date for that is not correct. But, this one I will, yeah, I can just update it now, so you don't take so much time. So now it should be. Thank you. Now you fix that. Yeah. So the P, Q, and R, they have a quorum, and they all proceed to the timestamp 2, and for the timestamp 2 the value is y, but this the value or the R, S, and T is another quorum, and they might have a quorum for timestamp 1 still, so that the read can return the old value. So this is another example of a non-valid execution flow, and here are some more invalid execution flows that you are first reading the new value and after the old value, and yeah, the same thing on the lower part. And here we have valid ones. Here is what we want to happen: that we read the old value and we read the old value and then new value. So this is an allowed execution flow, and also in this case that we are just reading the old value every time. This is also allowed because it's only after the write has terminated successfully that we have some guarantees that we will read a new value. So all of these read operations, they started before the write operation terminated. So that's why we can not have a guarantee that we will write the news or read the newest value. And yes, so we have more execution flows. This is also valid atomic executions. Yeah. So the algorithm for implementing something like that, it's the idea is that when you do a read, then you do what they call here like impose, that you read and then you send out this read to everyone else, and you attach with the value that you read and plus timestamp. So that when others receive that read, they can update their timestamp, and they can have the locally kept timestamp and value, and they can send acknowledgement for this. So that's the main idea of this algorithm, that yeah, you write and then you broadcast to other ones what you write with the timestamp. And similar for the failed silent model with we have the majority voting. So this one, it has the same idea that when you do a read, you also broadcast to what you read, and yeah, you do a check for a quorum, that if you have a quorum of reads, then you broadcast the write. If but you also check what the timestamp here. So the only we will broadcast the ones with the highest timestamp that you saw. Yes. So this is a one N, so one writer and one N readers, and it will have four communication steps for reading and two for writing. All right. And then the next is the NN atomic registers, which has multiple writers and wait, excuse me. The difference here is that we now allow for multiple writers, and it also have the properties that a read shouldn't a read concurrent with any write should return the last value written. So previously we allowed that you could return either the last value written or the one currently being written, but for the NN atomic register, we want to read to the read is not concurrent, returns always the last value written. Yeah, and we have the module description. And the determination property is the same as the one writer or reader atomic one N atomic register. But now we have also the atomicity property, and they when we have the atomicity property, the failed operations appears that they must either be fully complete or not invoked at all. And it appears that they happened in just one instant in the execution. Yes. So the idea here for this part, it's kind of similar in implementation from the multiple readers that where we like broadcasted or imposed our read on other processes, but now we don't impose the write, but we consult the write. So the code they have for this is like a majority voting, and the parts here with the read, they are similar, but the new parts here with the write, where you only trigger the write return or the read return when you have a quorum of acknowledgements. So in the previous algorithms, if we go back and guess yeah, they didn't have the similar step here for the read return. All right. So any questions about the NN or the atomic registers in general? Because if we don't have any questions, then we can move on to the consistent global state, which is another topic. That I have for you somewhere. Let's see if I can find it. Yes. And can I make this full size? So yeah, all right. So now, yeah, so this is a well, a presentation about global states and with time and ordering of events, and it's from Alberto Montresor, which is a well-known actor and well-known in the community. And yeah, this is, I guess, his presentation that we are now using. So we are doing that, but yeah. So the so this one I believe I can go through, and it has some maybe some difficult parts with some events and the timing. So if it's not clear, then just stop me and I will try to explain better. So yeah, it contains the definition from a distributed algorithm that it's a collection of distributed automata, one per process, and a partial execution of a distributed algorithm. This is a finite sequence of events, but infinite execution, this is infinite sequence of events. So usually we concern ourselves with finite sequence, and it's abstracted in a way so that we have only a send and a receive, and we also have some local events that can change our variables. So this is the very high level abstraction of a system or a process. So so the idea about this presentation is to give some introduction to how we can keep track of time and events in distributed algorithm systems, and the way that we can do this is to keep a local history of E1, E2, etc. This is our events, and the I here, it denotes like who for which process is this event. So for example, the I can be 1, and then this is for process 1. Yeah, so I guess it says in the next line what I tried to explain. So the K, it's the prefix of the first event, and the I is the process index. Yes. So the history of the events, it doesn't capture the ordering of them. It just captures like when did you receive them, but if you want to add a notion of timing or ordering between events, then we can try to do that. But first there is the definition that happened before, and what you probably remember from one of our earlier lectures where we saw the exact same thing, where we have like the happened before, like one event happened before another, and there's 3 scenarios where this can happen. So the first one is obviously if both events are executed by the same process, then it's easy for that process to say which one of them happened before. And if an event is a send, and then somewhere there is a receive event that was triggered by that send, then we can also say that that send must have happened before the receive. So I hope that's clear, that you cannot have a receive before you had a send. It would be very strange. Yes, and then we have a transitive property that if there can be an intermediate event here. So, for example, if an E was a send and E double prime was a receive, and then E prime was another local event that was executed by the process that received the message, then we can say that the send happened before that local process, because we use that intermediate double prime event to have this relation. Yes. So here is a typical space-time diagram that we will delve into further, but here we can, for example, we can say that E11 must have happened before E23, because E11 is sent that message to E23. Yes. So for example, I'm trying to see if there's yes, we can, for example, E31 and E22. We cannot say which one they're happening concurrently, but we will see more examples later on. So yeah, the happened before, if the event E happens before the E prime. That means that we can find a series of events E1 up to En, where E1 is E and En is the E prime. So this is the transitive property. Yes. So all the intermediate events, they have one of these two properties. Oops. And yeah, if they are not concurrent, no, if they didn't happen before, then they must be concurrent. And we write this like with two bars. So it's like the or symbol in Go. And yeah, some homework to try to prove or disprove that this is transitive, and well, we can see without too much effort that it cannot be. So we have, for example, the E11 happened before the E23, and so okay, we will see it later on. It's more clear. It'd be easier with the blackboard, so it should draw something. But okay, we'll see. So we have the local state denoted with this sigma, small sigma, same superscript and subscript implementation. And then there's the global state, which is the tuple of all the local events. So each process has a local state, and the global state will be the sum or the collection of all of these, so the big sigma. And then they define a cut, and a cut, this is basically you cut the execution flow, and I have shown it here that the execution flow, this is kind of just cut. So each cut, it has a global state, or at least a collection of local states, and yes, it's the union of partial histories, one for each process. So the history for P2, it has these events, P1 has these events, etc. So what you do in these cuts, you go up onto the line here, and everything that happened on the left side of the cut, it is like included in the state, and everything on the right side, it didn't happen from the point of view of the cut. The same thing with the C. So typically in the exams for this course, there would be like a question regarding this, where you will be asked to either answer what processes are concurrent or happened before, or you would be given like draw a cut so that such and such processes are concurrent. And if a student, for example, drew this C prime on the exam, then he would be in trouble, because you can see that he has it's drawn here a cut which has captured only the send the receive event, but not the send event. So this cut, it cannot kind of correspond to anything realistic, or it's like what they say, an inconsistent cut. But for the other event C, it has like the send event, but it doesn't capture the receive event. But this, of course, can happen, that you can have a send, but the receive didn't happen yet. But you cannot be in such a world that the receive happened, but the send didn't happen. So that's an important thing here. Yeah, they impose the same questions about the real state. So I guess I already went through this. So cut is consistent for all events E and E prime. E is a subset of the cut, and E prime happened before E, thus E prime is also in the cut. Yeah. Okay, so that captures the thing with receive. Yeah, and it says there explicitly, all messages must have been received before, must have been sent before. Yes. So that's that. So so they have another definitions with predicates, or not a definition, but they say that if you have a consistent cut, meaning that it's like it corresponds to a real execution, a possible execution of the system, then you can evaluate predicates in that consistent cut. And they denote predicates with this phi. I guess this is a phi. That's an F. And if you can have a predicate evaluation, then you can do some cool stuff, like the garbage collection, or in the sense that in this case a distributed garbage collection, deadlocks, cross debugging and monitoring. So yes, this is motivation, and I guess you all know what's a deadlock, and probably you could face it in the labs. But yeah, it's like two processes, or it can be more than two, but they're like waiting for each other. So you can have they're both waiting for the other one to release the lock. And here you have a difficult case for garbage collection, because the object reference is referencing back, so it can be difficult to know when such an object can be garbage collected. So why is it difficult with the global predicate evaluation, GPE? So this is the same arguments that you find in most uh, text with distributed algorithms, that they have an issue where the latest data that you compute or what you reserve, that it can be obsolete. It can be inconsistent. And you need maybe some consensus algorithms to make it consistent. And it can be incomplete, that you didn't capture all possible events. This is some challenges with this. So this one can skip. Deadlocks, yeah, I'm sure you know deadlocks. So then another definition, a run. So what is a run on a global computation? That's a total ordering of the events in a history. So yeah, so this is like a run of the history of the events in the history. And it can be many different runs. As you see here, they have this change somewhere. First E1, 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 E2, E1, E3, E2, 1, E2, 2, where is it? Here, and 2, 3. So the, I guess this one is, they should be changed. 3, it should be 3, 1, 3, 2, 3, 3. Anyway, the and this one is like round robin run, and there's another one here, E1, E2, E3, E2, 1, and E2, 3, and E3, 3, I guess it should be 1, 3 again here. And anyway, the idea here is that both of these are like runs, like both of these are possible ordering of these events. So that since they are concurrent, the E11 is concurrent with the E12, for example, then we cannot reliably say that E12 must happen before E11. That's the idea of these ones. And as you can kind of use these runs to evaluate your system. Yeah, so to monitor the processes, we have a distinct process that is doing the monitoring, and we call this an observer. So the sequence of events corresponding to the order in which notification messages arrive at the monitor is called an observation. Given the asynchronous nature of our distributed system, any permutation of a run R is a possible observation of it. So again, this it's any permutation of a run, meaning that any ordering of the events can be observed, but we restrict some of the runs so that we are only interested in those observations that are consistent. And for example, if we have a send or a receive before a send, it will not be consistent. Okay, yeah. So in day-to-day life, we capture the causality of events by simply using the time. And yeah, they have an example here that you withdraw some money at the ATM at 1 o'clock in Trento. Then only 20 minutes later, you cannot have flown all the way to Paris and also withdrew money. But yeah, maybe in the future it will be possible to travel so fast, but we will see. So anyway, in the distributed systems, then we don't have a 20-minute delay on events. They happen, every milliseconds or nanoseconds. So there's a lot more events, and the time between them is very much smaller. And this is like kind of why it's not feasible to use a real clock to try to achieve a millisecond or nanosecond synchronization. Just because just the network communication can be too slow, and so we want to get a tool to assist us in having this causality, but we cannot rely on physical clocks. So what was like one of the first idea with this is from the Leslie Lamport, which was the inventor of the Paxos algorithm. He also had a paper regarding logical clocks, which does this exact thing. But I think that we can we can continue a little bit more, and then we'll have a break. But okay, so logical clocks. You kind of already implemented this with the round system in the Paxos labs. So this is a very basic implementation of a logical clock, in the sense that it's always increasing, and you know that round 100 must have happened after round 50. So we can, well, actually it's depending on the behavior of the proposers. For example, like we said in the start, if you have very start that if you have a lot of leaders, they're all proposing, then that assumption can be not true, because one or two processes might be competing for the leadership, whilst the other process can be just listening. But for each process, that one process can say that if he sent a message or prepare with timestamp 10, and he sends again with 13 and then 16, then he can know that the 16 happened after 13 and then after 10, etc. So this is the definition that they have here. So the LC, logical clock, maps an event from a distributed system execution to an element of time domain T. So this is very fancy, but like I explained now with the Paxos example, that they have. We can say that one event, if one event happened before the other one, then the time spent time of the first process must be lower than the second process, but we cannot go the other way around. But I guess it doesn't say here, but yeah, the example that I explained, it doesn't have the strong clock consistency. Like we cannot say reliably that even though the timestamp is higher, then the process must have happened in such an order. But we can say if we already know the ordering of the events, then we can say something about how the timestamp will look like. So it's important to see the difference that it's only a one-way. It doesn't have a strong clock consistency. Okay, all right. Sorry. So yes. So what I explained or suggested is the scalar logical clocks. This is Lampert's idea, and it's monotonically increasing. Each process keeps its own local clock, and the messages carry this timestamp in the prepare. But yeah, what we don't have fully, but we kind of have it, I guess. In the implementation is this step here that you increase the clock by 1 whenever it was sent or you have another internal event, and then when you receive something, you check the timestamp of that message, and then you update the local one. So if you receive a timestamp from something higher, then you update your own local clock. Plus you add 1. All right. So here is well, how the local clocks would look like. And for example, you can see process 2, it goes from 1 and then jumps to 5 because it received a message from 4 and then updates its own local value plus 1. This is 5. And similarly, process 1 goes from number 1 to 2 and then to 4 because it received a message 3 from a different process. So this is all great, you can see, but yeah, so as I said, it satisfies this simple or this clock consistency, but it doesn't satisfy the strong clock consistency. So we can see that where do we have a great example of so if yes, let's see. For example, this 4 is lower than this 5. So the local clock for process 3, it's 4, and also the local clock for process 1 is 5, but we cannot. There's no causality between these two. So these 4 and 5 here, they are concurrent. That's why we don't have the equal, or the implies it doesn't apply this. But the other way, that if we know that 4 causes 5, then we know that 4 must be happened before 5. I hope that's clear. So to satisfy the strong clock consistency, we can have a causal history captured by this, I guess this is theta, if someone knows. But let's just check this very first. Talking about theta. Yeah. And so the theta of an event is it's a set of events that happen before this event. So for the events in the history, all the events, they happen before this event. First, we do a union with ourselves, so it includes itself. So the proof, it's compactly written here, and well, it says that for all the events that's not E prime, so all distinct events, such that the time stamp or the clock is less, then the definition says that this implies by definition that the theta is a subset of E prime. So by this definition, so by this definition here, that if the E prime happened after the event E, then event E must be a subset of E prime. And this implies that E is a subset of this, or not a subset, but in this set. So we see that it's in this history. And this implies that by this here, that it must be in that set, or it must be happening before. So yeah, let's do this example before we take a break. Okay, we have one question. Does this timestamp tell if events are concurrent or not? So where? This one. Yeah. So this one, it tells you that they are so the idea of the timestamp, you need to check how are they used. So because you have a strong clock consistency and just a clock consistency. So if you have a strong clock consistency with this causal history, then the time stamp tell you that they are not concurrent. That if the timestamp for E is lower than E prime, then you can say that uh, E happened before E prime. If they are equal, then you can say that they are concurrent. So the idea here is that you can use this timestamp to more easily see which events are concurrent or not. But yeah, if you have only only a clock consistency, then this will not tell you anything really that you because this is just a local clock, and even if it's lower than another process local clock, you cannot say something reliably about causality. But if you have a strong clock consistency, for example, with this theta that we saw, then this implies goes both ways. So, so if you have a causal history, then you can say that this goes both ways. Well, how could you implement a causal history? Like, for example, here, you can keep track of all the events that happen in the history. But it's, I think we saw one algorithm that kind of did this, that they sent the whole history in each message, and you can imagine how fast this would grow if you, in every message, you had to attach all the history to each message. It would clearly not be scalable. So what's done is that we have what we call a vector clock, and I will continue with this in 10 minutes. So if we have a 10-minute break, then so I can have some water for my throat, and we will continue with this vector clock, and you will see how great this is. So let's just, if we can continue in 10 minutes, it will be great. Hello, hello. Okay, so are we ready to continue with the interviews? I hope so. Mm, So, um, um, yes. So where did we leave off? Uh, with the vector clock. So the vector clock. This is similar to the logical clock, only that now we are keeping track of all the processes, not just our own, but all of them. So we have a vector clock for an event for I, which is the um, process I. So for each I, you have a memory slot, let's say, or an average slot. Um, um, so the theta, this is a cut which is consistent. That there are no inconsistent events in the theta. What is the causality? So yeah, each process maintains a vector clock, and whenever an event is executed, uh, the vector clock updates the value of that or the vector clock of that event. So it's updated like this, very similar to the this thing we saw for the logical clock. That if you have an internal event or a send event for your own process I in this example, then you update it by one, you increment by one. But if you have a receive event where you receive a message from a different process, then um, you update the vector clock um, to the maximum that you receive attached to that message. Yes. So, but if you send to yourself, then you do the same that you would have done for the send event. All right. So it looks like this with three processes that all of them have. I guess they start by all zeros, and when they do an event, they increase the clock for um, for for themselves. Um, so, for example, the process one, he um, triggers a send event, and because of this, he increases. Oh, by the way, so every slot zero refers to the process one. The array slot two refers to the process two, and the last array slot refers to the last process. So for the point of view of P1, the other processes didn't do anything yet, and here's the first one that did something. So he increments his own timer and he sends the message. However, when P3 receives the message, he knows that well, he has already done something, and now he's doing another event, so he's increasing his own clock, and then he is updating also the clock from process 1, because process 1 attached the vector clock to the message. So another example is here. The clock for P1 is now 2, and the clock for P2 is 1, and for P3 is 0. But when the message is sent from P3 to P1, the process P1 updates to he increments 1 for himself. He keeps the value for P2, and then he takes the value for the P3 that the process P3 attached. So now his time will be like this. So I hope this is understandable. And well, you can see that it's possible to have very large jumps. For example, here it jumps from 1 to 5. But it's because he didn't have any messages that I guess told him about the clock for P1. And another example, it's yeah. So yes, because now we are looking at the vector clock. And the vector clock, it has the strong, as we will see that the vector clock has the strong clock consistency that we couldn't achieve with only local clock or logical clock. But with a vector clock, vector logical clock, then we are not only keeping our own time, but we are keeping like the time of the other ones, or at least our view of their time. So in that way, we can get that property. But you see here that we have the time 1, 2, 4, and when we get the message 413, we don't update the timing for the P3 with the 3, because we have already a higher value from before. So this is always it's like a monotonically increasing type of algorithm that it will never go down in value. It will just increase. Okay, so anyway, there is some fancy mathematical definitions there that can be cool to know about. So first off is how can you say that one vector clock is less than another one? So this, if one is less than the other, this implies that they're not equal. And for all k, meaning all the, I guess, processes in your vector from 1 to n, so you have n processes, and here it's not zero indexed as we usually have in programming, but for every clock in vector v, it is less or equal than for the v prime. So yeah, I would really suggest to you that you get familiar with reading these types of definitions for your project. Yeah, and now you can see that we have well, the strong clock condition, it implies that the vector clock um, mm, so if one event is happens before the other one, this implies that the vector clock is less uh, from the first event to the second one. And it also implies that the causal history is a subset of the E prime. And well, there is also a simple strong clock condition, which don't know if this is any value, but so here the event of I guess process I to process J. This is so that the vector clock for that specific process, it's less or equal. Yeah. So then two events, they are concurrent if and only if so here they have kind of, I don't know why, but they have switched the inequality signs, because here we have less than and less than, but someday now it's greater than. So I don't know what's the exact purpose, but so now EI and EJ, if the event I is greater than, so just to be clear, now we are talking about a specific index here in the vector clock, right? So for the event I, for the index I, it's greater than for event J for the index I, and for the event J, the event J is greater than for the event I. So none of them happens before the other. Yeah, so can we find any example of this? Well, I didn't see. For example, if we have 124 and 413, can we say that, for example, yes, we have, we can find numbers that are not matching, right? So 4 is greater than 1, but 1 is less than 2, and 3 is also less than 4. So for these two events there, 413 and 124, they satisfy this predicate here for the two first events actually. But if we try to check this for something that we know is concurrent, then for example 5, okay, this is not greater than 5, 1 is not greater than 1, and 3, this is not greater than 6. So these two are, they are not concurrent. So is there anything more complex? Can we say, for example, yeah, we can see that there is a message from P2 goes to P1, and then it goes blah blah blah, and then something to ends up at P3 at the very end. So can we say that this event here, at P3, it happened before P2? Well, let's first we can see if they are concurrent. Okay. So is one greater than 5? No. 1 greater than 1? No. 0 greater than 6? No. So we see that they are concurrent. But other example of concurrent event, we can let's use our imagination here. For example, yes, we can have, for example, this send event here. And did it happen before yeah, this one even, or this one? Well, is 1 greater than, or 0 greater than 1? No. And then we have 1 is greater than 0, yes, and 0 is less than 4. So this event at P2, it's concurrent with this event here, 1 or 4, and also with this event, and also with this event, and also with this event, and this event. Yeah, but not with the last one. So does it make sense that you can use this vector block to find which events are concurrent or not? All right, I hope so. And then we have something with the cuts again, that the two events they are that are not equal are pairwise inconsistent if either one event happened for the so at one event the index or the view is less than the other one, or for another process they are. So if there is one this less than, if we go back to this definition, if for all the events it's less or equal, we can have this pairwise inconsistency. And now I don't have a blackboard, but if we had the cut from before, where we had kind of included the send, but not no, we have included the receive, but not the send. Then we would have a pairwise inconsistency, because we will this will not capture that we have, for example, this 513, but we had the 516. So that's that. And again, the cut is consistent if it doesn't have any inconsistent or pairwise inconsistency. So yeah. Let's see the global predicate evaluation. So at each event, each process sends a notification to the monitor describing its local state, and the monitor collects notifications to reconstruct an observation of the global state. And so the observation can be one of these thing, consistent or not consistent, or not even a run at all. So that's obvious. So let's skip to the message ordering, and we already had a look on message ordering with the FIFO order, first in, first out, and here they emphasize the point that a receive is not a send. So what we did, or what we saw in the FIFO ordering, is that we allowed to receive messages, but we would not deliver them until that we had received all the missing ones in the sequence. So we needed to have a consecutive order of messages before we would deliver any message. And so I hope that's clear also. So yes, the FIFO ordering keeps a timestamp, then so it knows which message is the next one to be delivered, but it can receive messages in the meantime, but it will just put them into a buffer. Yes, so let's see if there's something important to say about this. So I wonder if we can I guess we can. Okay, so if we try to have a monitoring with the real time, and this part is kind of motivation for the problem. Just keep that in mind. But then we assume that there is some time delta, that we have some insurance that the messages must be delivered within this time. But then yes, I will see that in a distributed system we cannot have these guarantees about real time. So it's only we can only have a definition about real time if we assume that all messages must be delivered in that order, or it must respect this this delta. What do they call it? Yeah, just within time delta. But yeah, it says here that the real time clocks does not support stability. It's the maximum delay of messages that enable it. So instead, we use logical clocks to have this feature. So messages, they will be delivered in order that respects the timestamp. And yes, we saw this clock condition already. Um, um, and again, if it's just a clock condition or a simple clock condition, it doesn't imply that if the logical clock is less um, between two events, that you can say something about the ordering of the events. It's only if you know the ordering of events, you can say something about the logical clock. Um, so, um, so yes. So the concept of delta, time delta in an asynchronous system must be kind of reproduced in a logical way. So, and that this is what we do with the timestamp. So, or at least with the vector clocks. Yeah. So let's see. We already covered this parts. And we can take a look at a snapshot. So this is important idea in distributed computing, that you can snapshot the state of the system, or you can make a photograph of the system at any or specific points in time. So this can be like a checkpoint. You can also call it, but or like a save. But it allows you to recover from failures. You can recover from a previous state of the system. And in garbage collection, you can use this. So it's always a challenge that if you allow each process to take a snapshot, then how do you kind of ensure that they took the same snapshot, so that they don't recover in different states if there was a crash or restart. So again, Lamport has, when you read distributed algorithms, you will find him many places. So how can we have a snapshot algorithm? And this assumes that processes communicate with each other through FIFO channels. So whenever there is a message that has been sent but not received, then they are stored in the channel X. So X, Y, J contains all the messages sent by PI but not received yet by PJ. So they are like in this channel, and reversely, the JI channel contains the message sent by PJ but not received yet by PI. And yeah. So you know from Golang that they have also a channel type abstraction that I'm sure you are familiar with. So yeah, this algorithm assumes that the channels satisfy the first in, first out order, and yes. So I let's see if this is so interesting. All right, let's go fast through this. So the snapshot protocol is presented in three versions, where the each version builds on the previous one to remove some of these assumptions. So the first one here is using this delta time. So the snapshot is like the process chooses a time that's far in the future, like you just say, okay, 1 week in the future, or whatever it's defined as. And then it broadcasts that, okay, everyone must take a snapshot at this time or this moment. So this is what the first version does. So then the idea from drawing from the version 1 to the version 2 is that, is there any way that to remove the dependency of the real-time clock, and instead of having the delta time, then there's a kind of a construct so that whenever the local clock reaches a specific time, you can do something. So yes. So here we assume that we found a logical time large enough that a message containing it sent by the process 0 will be received by all other processes by before TS. So again, there's a delta time, but this now the delta time is with respect to with respect to events or local clock events. So here we are choosing a large logical time that's far in the future, and again it sends out this message to all the other processes to take a snapshot at this time, and that's what it does. It's broadcasted, and then the next final version is to remove the need for this timestamp completely. So yeah, this is the idea is that the process just sends the snapshot to itself, and when it's receiving or did finished taking a snapshot, it sends the snapshot message to all processes, all other processes. So this can work whenever, or since we assume that the messages are ordered in the channel, types of hyperorder. Yeah. So I think that that's that. So with the predicates, yeah, we can call this. Okay, so the sigma is like the global state that we discussed previously. So it represents a state of the past, potentially with no bearing to the present. So that's the thing. Doesn't so given this global state, does it make sense to evaluate the function phi on the global state? And yeah, there's some typical system that remains true whenever they become true. Yeah. Okay. So the last, I think the last important definition that they have here is the leads to definition. So before we had the happen before with one specific event, and now we are looking at the state itself, like what is the system state. So a run or a persistent run, this is a sequence of events that is again causing or leading to a system state. So we can say one state leads to another state in a specific run R, if either R is the sequence of global states, or the sigma is state I, and sigma prime is a J, and then the first state it was like before the other one in that one. So that was clear, and they compute a lattice from these states. So path of in the lattice, this is a sequence of global states that is corresponds to a run. So the a lattice might look like this here, and we can see here that okay, we start off at event or state 0, and either the event let's see, and the event what's the index here? The K. They say what is the level of the, oh, okay, so for the second level up, yeah, makes sense. So for the second level here, so we have the first level 1, level 2. So I think that yeah. So the first number here, it's the state of the first process, and the second number on the superscript, this is the events of the second process. So what you have is that either the event from the process number 1 can happen first, or the event from process number 2 can happen first. So you have two possible runs that it is possible. And after then we see that we have a consistent run if we allow the P2 to execute all its events first, because the P2 doesn't have a receive event until the very end. So we can have that first this event happens, next this event, next this event, and finally this event. And now we have done all the 4 events here, but we cannot have the last event before this 3 here. So you will not find a path in this lattice that goes from either 0, 1, or 2 till 5. So we can see that the only places that we have the event 5 in the global state is on these 4 last here, and they're all preceded by having this event first. And similarly, we cannot find any path from a 0, 0 to this event. So it only allows that at least one event must have happened on the P2 before this event happens. So we have that this event can happen either after this, or after this, or after this, or after this. You see this here. You can go for any of these, then yeah. And finally, we end up in the final global state where all of the events have executed. So I hope that's clear. Yes. So yeah, some definitions. Great. So I don't think we will go into the details with the pseudocode here, for the sake of your own time. So I think that yeah, if you want to read more about this consistent global states, you can go to the original paper. Yeah, it's an old paper, but it has all the fundamental definitions. And I think that we will end there. And then I think also that if you have any questions, you can be free to ask us. And now we are finished, or we have completed the curriculum or the syllabus in the book, and we finished this global states. So the next time I wanted to do a presentation on academia or code. I will see what, maybe both. But I will find a paper that you can read yourself, so that it will maybe be more interesting. So I don't know what format I will use in my presentation, because maybe I will just not have slides, or maybe I will just go through the important parts of the paper itself. But I think that this paper is only 6 pages, at least the short paper one, so it shouldn't be too much hassle to read. But yes, so I think that's that. The labs, it's only not 2 weeks or so until the deadline, but yeah. So if you need any help with the labs or anything, then just ask. And yeah. Yes, I will give this because I think this is a very reasonable paper. I will so what's the this one. Peer-to-peer information system based on the XOR network. So this protocol, very important in real life system. That a lot of system use this, or at least some modification of it. Yeah. So, but anyway, yeah, I will find the paper, so you don't have to pay too much money for it. So I'm gonna put the link. All right. So then, yeah, yeah, maybe it makes sense just to do the lecture on Thursday, because yeah, I will write anyway in the Discord if I need to change the file. Dockering is not a must if we use Python machine to quiz. No, you should do the Docker anyway. Like you should build containers, and then you can, if you are able to build the container, then you can present it on the Python machine. But I think the Docker part, that's not it's not so difficult. You just basically copy this instructions there, and you run the command, and it's maybe you need to modify if you change your name of your application, or something like that. You have a special boot process, but yeah, the main idea is that you get a little bit familiar with Docker. We don't ask too much. Just yeah, install the package on your system and run the commands and have a container that's being built. And if you want to show your or present your lab on Peter, that's fine. We will not investigate in the details about your container, but at least show that you are able to download the Docker package or application and run these commands. So that's it. Okay, okay, then yeah, we will see you next time. Have a good day. Bye bye.